Example 3 is solving an exponential equation. So here we have a variable in our exponent. In order to solve that, first of all, we have to get our exponential part alone. So subtract 2. We always have to get the term with the variable all the way by itself before we can solve. So I'm dividing by 4 now. E raised to the 2x power equals 7 over 2 or 3.5. Now, to get rid of my e here, there's 2 different ways we can do this. Just like there were 2 ways we could do it with logarithms. I can either take ln of both sides, I can take my 2x and swing it to the front as a coefficient. And then remember that ln of e is going to be just 1 because this is log base e of e. Just 1. We get 2x equals ln of 3.5. So just like with logarithms where we took the log of both sides, we can do that here as well. Or I can switch to exponential form. Log base e of 3.5 equals 2x. Then remember, log base e is just ln of 3.5 equals 2x. So either way, I get to the same spot. From here, I divide by 2 and get x by itself. So x equals exactly ln of 3.5 divided by 2, which is going to be approximately, when you type this in your calculator, okay, ln 3.5, make sure you close that parenthesis before you divide by 2. And we get 0.626. Our exact answer and our approximation there. Go ahead and try the first one on your own. Okay, ln e to the x minus 2 equals ln of 12. To get rid of a variable in our exponent, we have to switch to logarithmic form. And since our base is e, we use ln's. Swing that to the front. And since we're multiplying by that whole quantity, we put it in parentheses. Ln of e is just 1 because it's log base e of e. And again, this is the exact same place that we would have gotten if we'd have taken log base e, or ln, of 12 equals x minus 2. And that's because we did log base e of 12 equals x minus 2. So either way, again, it does not matter which way you go. We're going to add 2. Ln of 12 plus 2 equals x. Big thing to remember here, guys, is that ln of 12 is one number. We don't know that number yet because we haven't typed it in, but that's one value. We can't add that 2 to the 12. Okay, these are 2 separate things. So now we take ln 12, make sure again you close that parenthesis and add 2, and we get approximately 4.485. You can try the second one here. To get our variable by itself when it's in the exponent, we have to get that term by itself first of all. Get that factor alone. Then switch from an exponential form to logarithmic form. Log base e, which is ln of 10, equals negative x. Remember, our logarithm always equals the exponent every single time. We can divide by negative 1 here. And we get ln of 10. When you divide by the negative 1, just makes the whole thing negative. Which is approximately negative ln of 10, negative 2.305. 3. Remember how we said with logarithms we can't have them equal a negative number? It's fine with an exponent if it's negative. Here it wouldn't be because the negative times the negative here would give us a positive, but in exponential form it's okay. Remember our domain there is all real numbers. We can have any x that comes up. Let's try the last one here. First we have to get our exponential by itself by subtracting 5. E to the 3x power equals 10. Now because we have that variable in the exponent, we have got to switch to exponential form. Ln of 10, which is log base e of 10, equals 3x. Divide by 3, and x equals ln of 10, the whole thing divided by 3, which is approximately, don't forget to close that parenthesis, 0.768. Example 4 here is on page 480 in your textbook. There's also a picture there, so you're going to want to have your textbook out to look at while we're doing this one. A spacecraft can attain a stable orbit 300 kilometers above Earth if it reaches a velocity of 7.7 kilometers per second. The formula for the rocket's maximum velocity v in kilometers per second is v equals negative 0.0098 t plus c times ln of r. The booster rocket fires for t seconds, and the velocity of the exhaust is c kilometers per second. The ratio of the mass of the rocket filled with fuel to its mass without fuel is r. Suppose the rocket shown in the photo on page 480 has a mass ratio of 25, a firing time of 100 seconds, and an exhaust velocity as shown. Can the spacecraft attain a stable orbit 300 kilometers above Earth? So there's a ton of information here. We know that it needs to reach a velocity of 7.7 kilometers per second. And then we know some values here. We know that the mass ratio is 25, and that's our R. We know that the firing time is 100 seconds. That's our T. And the exhaust velocity, C, is shown on the picture on page 480, and that's 2.8. So, C here equals 2.8 kilometers per second. We can plug these into our formula. V equals negative 0.0098 times T of 100 plus C is 2.8, ln of R is 25. We can type this in our calculators. Negative 0.0098 times 100 plus 2 ln of 25. That should be 2.8 ln of 25. And our V is going to be 8.03 velocities in kilometers per second. So that's not what the question is asking. What the question is asking is, can the spaceship attain a stable orbit 300 kilometers above the Earth? So what we need to do is we need to compare this to the 7.7. It says that it can attain a stable orbit if it reaches a velocity of 7.7. Our velocity here reaches 7.7 and then goes a little bit further. So can this attain a stable orbit? Yes, because 8.03 is greater than 7.7, greater than or equal to. Now, a booster rocket for a spacecraft has a mass ratio of about 15, an exhaust velocity of 2.1 kilometers per second, and a firing time of 30 seconds. Can the spaceship achieve a stable orbit 300 kilometers above Earth? Remember, our formula here is V equals negative 0.0098 T plus C ln of R. we have 15 as our mass ratio, which is R. We have an exhaust velocity of 2.1, which is C. And we have a firing time of 30, which is T. So we can plug those in here. Negative 0.0098 times 30 plus 2.1 ln of 15. Go ahead and type this in your calculator. Negative 0.0098 times 30 plus 2.1 times ln of 15. Okay, here I got 5.39 kilometers per second. So, can the spacecraft achieve a stable orbit 300 kilometers above the Earth? No. And it can't because 5.39 is not greater than or equal to 7.7. And that's what we need. We need the kilometers per second, kilometers per second to be at least 7.7 in order for it to attain a stable orbit 300 kilometers above the Earth. Here's a real quick recap on this section. The function y equals e to the x power and y equals ln of x are inverse functions. What that means is a equals e to the b power, then b equals ln of a. The exponential function y equals b to the x and the logarithmic function y equals log base b of x are inverse functions. That is our last section of chapter 7. So these will be your last notes for this chapter. Here's the assignment. You do not need to start this. We will work on this Thursday in class, but it's there just in case.